from January 2024. Turns out this hasn't really changed. This was actually one of the first modern instruments that was developed for organic chemists. It gets used mostly in organic chemistry.
Okay.
For a couple reasons that will make more sense in a minute. It's based around an earlier version that worked for any element that could basically just look at, where you basically took a sample and you burned it and destroyed it, and you looked at the color of light that came off, and you could turn that into what elements were present. They call that atomic absorption spectroscopy. If you're trying to differentiate, though, the structure, that wasn't very helpful, because when you're just going to find out you have carbon, hydrogen, and oxygen, which everything organic has carbon, hydrogen, and oxygen. So what they figured out they could do is, instead of just burning it, they could get to sort of some of these intermediates that are kind of happen when you burn something by just throwing really high energy electrons at it and blasting it apart into pieces. So it's going to work a little bit like if you had a giant Lego Hogwarts and you threw baseballs at it and then tried to analyze the pieces to figure out what it was.
Okay.
So you're going to get a lot of random pieces. You're not going to necessarily get the perfect structure necessarily, but you can definitely tell, okay, this is a tower. This is a Harry Potter figure. This is whatever. So that's kind of how it works. At anything organic, and an organic molecule. At Harry Potter. Right. So for instance, the way that the first step is basically, okay, let's say we had acetone. We just fire electrons at the acetone. And what usually happens then is we knock an electron off of the acetone. So we wind up with a really unstable molecule that's both got a positive charge because it lost an electron, which also means it's got an incomplete valence, which also means it's a free radical in a lot of cases. So it's got a lot of things going against it, suggesting this is a really unstable molecule. And what happens when you do that is basically everything falls apart. You start wind up with these other fragments, because basically you're not going to want to have something that's both got a charge and a free radical on the same molecule. So what winds up happening is it splits up into chunks where the free radical goes to one side, but the charge is on the other side. So, for instance, if this was our first molecule that we made, it might fall apart into these molecules, these fragments. We don't even call them molecules because they're so unstable. So they're more like an intermediate. Once we have this, though, once we have these charged molecules, magnetic charges respond to magnetic fields. Right? So all of a sudden, as soon as it's charged, we can actually apply a magnetic field to it and cause it to accelerate. Right? So the classic, the simplest version of a mass spec is basically a curved tube where you put an electromagnet around the curved part of the tube. So your sample comes in here. It gets hit with a whole bunch of high energy electrons, which causes it to fall apart. And then anything with a positive charge then is going to respond to this magnetic field, which causes it to curve. By varying the strength of the magnetic field, we can basically find the sweet spot that gets it to curve just right and stay in the middle of this tube.
Okay.
And then at the very end, it hits a collector. The collector basically can just tell something hit it. It can't necessarily tell how big it was. It can't tell what it was, but it can tell something hit it. And so basically what we do is we put our sample through, and then we scan the strength of this electromagnet so that at first, if there's no magnetic field, it doesn't accelerate at all, and it hits the wall over here, it sticks there. As the magnetic field starts getting stronger, it starts curving a little bit, and now maybe it hits the tube over here. But eventually you get to a sweet spot where it curves just right, goes right through the middle, and hits the collector. So if the collector knows what frequency, what strength of magnetic field is being used, you can work that backwards to figure out how heavy that molecule was. Because magnetic fields, what's the, if you know the force is based on the strength of the magnetic field and the weight of the object, right? Because force is equal to mass times acceleration. Well, by changing the force of the magnetic field and looking at what that acceleration is, because we can say, okay, it curved this many degrees in this amount of time, that work gives us acceleration, right? We can work backwards from the force and the acceleration to get the mass. We're not going to do any of that by hand.
Amazing.
This is the sort of thing that computers are really good at. You program it once, and then as long as the strength of your electromagnet is tied to something that can keep track of that and say, oh, collector just hit a spike. So we know that something hit the collector when the magnetic field was X strength. And so all mass spectrometry does is it measures how big the chunks are that correlate with specific magnetic fields. So what we actually get is something that looks like this. The nice thing about mass spec is that because we're dealing with atomic mass basically happens in whole numbers because we have to add up the protons and neutrons to add up to a whole number. As long as we're neglecting relativity, which we will for this kit, or for as long as neglecting, was it nuclear binding energy, which we will for this one. We're going to round to the nearest whole numbers for these. So we get this thing that looks like this. We got a bunch. It kind of looks like a bar graph.
Yeah.
Where on the bottom is the mass divided by the charge. For the most part, the charge is going to be 1. Because usually when we throw these electrons at this thing, we're only knocking off 1 electron at a time. So as a result, we get this spectrum. It's not really a spectrum in that it's not looking at light. It's a spectrum in that we scanned that electromagnet over a range, and then we looked at what came out. But it's not, we're not dealing with light. So it's not, strictly speaking, spectroscopy. But it makes something that looks kind of like a spectrum. And what this tells us is when we take this molecule, when we feed it through this mass spec, we get something that has a mass of 72 AMU. If we look at the molecular weight of this molecule, it's C5H12. Well, the mass of 5 carbons plus 12 hydrogens is 72. So basically, this is just going to tell us how big the pieces are. When we break apart a molecule, it turns into something that's 72 AMU, something that's 57 AMU, something that's 43 AMU, and a bunch of other stuff as well. And it's kind of hard to predict sometimes what the other stuff is going to be, but basically we're just going to chop off pieces of this and see if we get molecular weights that match up. And no, that's the part that we do. The computer gives us this. It says, hey, something hit the collector when we applied the right magnetic field that corresponds with 72 grams per mole. If we want to try and figure out what these peaks actually are, if we know what the starting material is, it's pretty easy. We basically just start chopping pieces off.
Right.
If we chop off a methyl group, what's the mass of a methyl group of a CH3? $15, yeah. We're rounding to the nearest one, so 15-ish is good enough. Well, if the whole thing is 72, if we chop a methyl off, we lost 15 AMU, right? What is 72 minus 15?
Yeah, I don't. I could do it in my head.
You could do it in your head. 57. We have a peak there. What's the difference between 72 and 43? So what chunk of this molecule would correspond to a mass of 29? An ethyl group, right? 2 carbons is 24 plus 5 hydrogens, it's 29. So basically, we took off this, if we took this molecule, if we chopped it in half right there and got rid of the ethyl group, this little isopropyl piece that's left has a mass of 29.
And the ethyl group
So the ethyl group is the difference. So to get to 43, so 43 corresponds with, here's the molecule. If we chop off an ethyl group, what's left is 43. So that's basically how the mass spec works, is by saying, okay, I'm just going to start from this material and I'm going to start chopping chunks off. And if it happens to correspond with a nice chunk we can pull up, we'll probably have a peak there. There's a small peak at 15, a small peak at 29. Right? And there's larger peaks at 57 and 43. So what that's telling us is that start from this, well, this is called the base peak. Or sorry, the molecular fragment. I'm going to try and make sure I use the same terminology as the assignment does. So the molecular fragment is you take the entire molecule and all you did was knock off an electron.
So it's safe to say that that's always going to be like our biggest number.
Your largest number-ish. There's a little tiny peak right there. What could that correspond to? What is it? What could possibly be contributing?
Could that be the one electron that got on top?
Not an electron, because one electron weighs so much less than any of this. What about the height? It basically means you have one extra proton or neutron. What, without changing the formula, what could change the mass of this?
Well, possibly. I don't know.
Not a lone pair. No, go back earlier to when we first learned about the periodic table.
Oh, the decimals that were ignored.
Yeah, what causes that 0.01 on carbon? That there could be carbon 13. There's about a 1% chance that if you grab the carbon at random, it's carbon 13, which is going to show up as a mass of 73, not 72, right? And same for hydrogen. There's about a 1% chance if you grab a hydrogen at random, it's actually deuterium, hydrogen 2. So you'll notice that right above all of these labeled peaks, there's a smaller peak.
Yeah.
For the most part, that's going to be what's called an isotope effect. And so here's the general gist of it. By looking at the mass of the fragments formed, we can assign structures to the various peaks. So the fact that we have a peak that shows up at our molecular fragment minus 15 tells us that it's easy to remove a methyl group. The fact that we have something showing up at our molecular fragment minus 29 tells us there's an easy methyl group or ethyl group to remove. Right, so it's a little bit like IR, where you go through and you label functional groups, except instead of labeling functional groups, we're labeling chunks.
Are some bigger than others? Like
What would make different? Go ahead, Taylor.
Like, what do you mean, like when they're growing with my?
Yeah.
So this means how often it shows up. Basically means that more of your molecules turned into this than stayed together as one piece.
Okay.
What might cause that? Why aren't all of these equal probabilities?
It's kind of harder and very complex.
And some fragments are going to be more stable than others too, right?
Oh, right, yeah.
Because if I had, say, CH3, CH with a positive charge, CH3 versus CH2 with a positive charge, CH3. What's different about those besides their mass?
Well, the positive charge is on a more substituted carbon.
Bingo. A secondary carbon having a positive charge is going to be more stable than this.
Mhm.
So even though we took this molecule and we chopped it right here, the side that gets the positive charge is going to be the side that's more substituted. The other side is not going to be a positive charge. It'll be a free radical, but free radicals won't show up here.
Okay.
Because this whole thing is based around using a magnetic field, right? You need it to have a charge for it to be affected by a magnetic field. Anything neutral doesn't get affected by that magnetic field.
Yeah.
So when we split this up and this side gets the radical, this side gets the positive charge, this side will show up as a mass of 43. And in that case, the ethyl group just continues going straight in our tube and it hits the wall. And so when we did this,
Let's put the sweet up.
I could, but I don't like that this projector doesn't keep it there. And so all my stuff, this one's not as well set up for that as that one. Good sneeze. Sorry, we tried to come up with secular ways of saying bless you when someone sneezes in one. Rigney Miller. Do you remember Rigney? His wife worked in the art department. She was an art student and he was a chemistry student just a few years ago. But his response was always good sneeze. I thought that that's a good non-religious way of saying bless you.
Congratulations.
Congratulations. Similar, yeah.
That,
No, I have not heard him say that.
no, but like, we took over our class and I just shot me, so she's so confused.
My favorite one is actually in Japan. They apparently say "go away, kitten" when you sneeze, because if you sneeze like in a really dainty way,
Yeah.
it kind of sounds like a little cat noise. And so when you sneeze, they say "go away, kitten."
That's really sweet.
I like "go away, kitten," but it doesn't roll off into these spells. Good.
Yeah.
So anyway, here's our molecule. When it splits up, so even if it looks like this originally, when this gets bombarded and hit with an electron, this bond might get hit. Maybe this bond only has one electron in it now, which means one of these molecules has to get a positive charge and have an incomplete valence, and the other one is going to have a radical, which is neutral, but also not stable. So when this bond breaks, you can make this, or you can make the reverse, where the radical is on the isopropyl group and the ethyl group gets the positive charge. So what that looks like then, this is the difference in stability of primary carbocations versus secondary carbocations is what's going to govern whether we have more things show up at 29, which is the mass of this molecule, or 43, which is the mass of this molecule. This is more stable than this one is, so we see it happen more often. We have two competing fragmentations. The one that gives us the more stable pieces is going to happen more often, and it's going to show up as a higher abundance, is the way that they call it. But basically, it's like how common is it? Let's see if this. There's a link to see if this will actually work. To an animation. Yeah, I have it downloaded. I'm seeing if it'll actually run though. It did? It'll try. It's a Java file. Yeah. Okay. So don't worry about that. We don't really need it. Yeah, don't worry about it. And so we can actually tell, we can see that this showing up if we look at methylbutane versus pentane. They're both going to have the same formula. So they're both going to have the same molecular ion or molecular fragment. But if you look at the relative numbers, it's different. The peaks have different height, right? Because 57 shows up really commonly here, right?
Yeah.
Which is, that corresponds to our molecular molecule minus a methyl group. Is there a way that you can take a methyl group off of this to get a secondary carbocation?
So like, what the top one is remember?
Right. Yeah, basically, sorry, we're looking for minus a methyl, not an ethyl in this case. So could you, in both cases, this 57 number is your starting material minus a CH3.
Right.
But no matter, the only way you can subtract the CH3 from this side leaves you a primary carbocation. Not very stable, right?
Right.
This molecule, you can take off a methyl group and you're still left with the secondary carbocation, which makes it more likely to happen. And so in both cases, the most commonly, sorry, this is the actual chapter from one of my lab manuals on mass spectrometry that has more background information, more details. And then this is the actual assignment. So some basic vocab, and then gives you some spectra, and then asks you to interpret it.
You said no experience driving Boston on the base
So base peak means something different. Base peak is whatever shows up at the highest percent abundance. So it's the biggest peak. So both of these have the same base peak.
Yes.
Because in both cases, the base peak is going to look like this, right? It's going to look like 3 carbons and 7 hydrogens, a propyl group. In this case, you can make a really stable propyl group by chopping off an ethyl, right? In this case, you can make a propyl group by chopping off an ethyl as well. And in that case, you're still making 2 things that are unstable, but at least you don't have a methyl. Remember that our radicals follow about the same stability rules as the carbocations. So we don't really want to have a methyl radical floating around either. An ethyl radical is a little bit better. So because a primary radical is better than just a radical all 100% by itself. And so the main gist of this is that when we're just looking at hydrocarbons, it's going to basically turn into, okay, what can I chop off? How are things arranged? If I'm only going to break it apart once, if I get to break 1 bond, what could I make? Does that then show up here? Turns out there's other things that can happen too, because once we make these things, sometimes they can rearrange. If we chopped this molecule up and we got a primary carbocation, it can shift the hydrogen over and still be the same mass, right?
Yeah,
And then you get a secondary carbocation.
yeah.
So we're still going to have some rearrangements that can happen. But the thing is, this whole process is going so quickly, going through that tube, that we don't always see those rearrangements happening. This is one of the few cases where you can actually isolate them as, for instance, a methyl carbocation or a primary carbocation. All right, some other key things we can look at. We already talked about that little peak right there, right? So anytime you've got something that has more than one isotope that shows up on Earth, then you can have some of these isotope effects. So this is actually one way that you can tell what's in there as well, because carbon and hydrogen, carbon's got about a 1% chance of having carbon-13. And I was actually off by a couple decimal points for hydrogen. It's a 0.01% chance of finding deuterium randomly. Some of these others have different ratios, though. For instance, sulfur is really interesting. Sulfur has a 95% chance it's 32, but it's got a 5% chance, which is a fairly large chance, probability, that you get something that's got a mass that's 2 higher.
Is it weird that it's like the 2 higher, not the 1?
So that all comes back to, remember talking about radioactivity in Gen Chem a little bit? Radioactivity and those nuclear reactions happened when you didn't get the right ratio of protons to neutrons, right? You basically made an unstable nucleus. The fact that this ratio looks like this, it just means that for whatever reason, the specifics of the strong nuclear force and the weak nuclear force, sulfur 34 happens more frequently on Earth than sulfur 33. So it just has to do with the specific element and the specific number of protons and neutrons in the nucleus. So it kind of is like its own little barcode. If you can separate these atoms and just look at, okay, here's mass, mass plus 1, mass plus 2, mass plus 3. If you happen to see something that mirrors those numbers, so if you were looking at your molecular fragment and you saw your molecular fragment and then a really, really tiny peak right here, and then something that was like 5%, and then another really tiny peak. Even that's not really to scale, because that'd be really small numbers, right? So 95 to 1 to 4 and then a tiny, tiny thing that might not even show up, you get that pattern. You've got sulfur. Even if you don't know that this is showing up at 32, because maybe something else is attached to it also. But the fact that you got this, if this is the molecular fragment, this smaller one, call that M+2. If they're in that 95:4 ratio, something close to 20:1, basically, that's a good indication that you have a sulfur. And same with some of these others. It's really, really easy to identify chlorine and bromine. If you have a molecule that has bromine, because bromine's two naturally occurring isotopes show up almost the same amount, and they're separated by 2 mass numbers. Chlorine are separated by 2 mass numbers, and it's a 3:1 ratio. So looking at what those little peaks are, those isotope peaks are, and what their relative abundances are can tell you what you have in your formula without even knowing it. And so here's an example. We don't know what this formula is. We take a mass spec of it and we see we've got something with a mass of 122 and 124 in relatively even amounts. What molecule do we probably have? You've probably got a bromine in there. And mass of bromine is 79 and 81, right? This 122 minus 79 . So basically, we have a molecule that once we knock an electron off the bromine splits. And our base peak is 43, which is a number that's already shown up, right? What's the mass of 43?
Yeah, that one.
Right.
Yes.
CH3, CH7, or sorry, C3H7. $36 from the carbons plus 7 gives us 43. So just by looking at this and looking at the isotope effects, and then looking what happens when we subtract off that really easy to recognize halogen, we've got almost guaranteed we've got some form of bromopropane. It's a little bit hard in this case to tell if it's going to be 1 bromopropane or 2 bromopropane, but we know we've got a bromopropane.
Okay.
All right, so this is also not it's not as much of a smoking gun as NMR. Proton NMR is still kind of the gold standard because it's got so much information. If you spend the time and you think about it right, you can almost always get to your complete structure from proton NMR, especially if you got a formula to start with. But if we have something like this in conjunction with proton NMR or an IR, this is still a really useful thing. And this is also similar to IR in that every unique compound is going to have its own fingerprint.
That's sort of.
So that's how the TSA machines work at the airport.
It's,
If you get selected for the secondary screening and they take that little cloth and they swipe the inside of your bag
oh,
and then they put it in the machine and it beeps to say you're good or you're not. Basically what that machine is a really cheap, not very specific version of this. Where it just does a quick mass spec and says, oh, you've got something that is kind of similar to the mass spec of C4. If that was the case, you're not going anywhere. You're going to stay there until they figure out what it is. Thing is, they give a lot of false positives because they're the cheap version of these. The really high-end version of these would be able to differentiate between, for instance, 1 propylbromine versus 2 propylbromine. So And that's in general what those machines are doing. The C4, it's an explosive.
Oh, in the carbon four.
No, sorry, C4 like the explosive. So that it actually happens. It happened to my dad once. My dad worked in the insurance industry, and at one point he had to go to a claim that was at a mine in Colorado where they were actively using dynamite.
Yeah.
And so he had like dynamite residue on his hands and clothes when he got on the airplane or when he went to the airport after that. And he happened to get selected for secondary screening that day. And so he took him an extra hour and a half to get cleared because they went through everything.
Yeah.
Because he was giving off a positive for dynamite.
Yeah.
Obviously, they don't want that on the airplane.
So is it really random selection?
Well, there's a social and racial question in there as well. We see this a lot. We fly in and out of Minneapolis a lot, which has a very diverse population. We never get selected for secondary screening, and it seems like every single time we go through there, we see a bunch of people with other colored skin getting selected for secondary screening. So I think that's less of a science question and more of a society question. But there's definitely that element that shows up. Like they don't have a way of doing the mass spec for that until you get selected for secondary screening. But there's all sorts of things that go into selecting you for if your name looks unfamiliar, or if when you're checking in, they decide that you don't look trustworthy, or your ID seems like maybe it isn't real. There's a lot of ways you can get yourself flagged, and sometimes it's random.
No arms. We're coming back from Mexico. And they were like, you can't go with her. And we were like, she's a minor, we're going with her. Oh my God.
Yeah, so like things like that are pretty random. We had Kuiper, the 3-year-old's bag got selected for secondary screening this last time, but I think it was because we crossed, his bag was in between a young black man and someone who appeared to be from the Middle East. And his bag was in between those two people, and they both got selected for secondary screening. So Kuiper's bag got selected for secondary screening as well. But then all they do is they do this, everything comes up fine, and you move on.
Right.
Assuming you don't actually have anything. It also does, this is also more of a societal government oversight question. They're not supposed to check for anything besides things that are dangerous to the flight. So they're looking for gunpowder, dynamite, explosives, that kind of thing. They're not supposed to be using that technology for any other sort of banned or regulated substances. So they're not supposed to check for drugs. Border Patrol might check for this. DEA. Right. So, but the lines of jurisdiction between TSA and the DEA are kind of blurry, and depending on what decade you're in and what state you're in, I don't necessarily trust them to keep that separation of powers. But again, that's not a science issue. That's a societal issue. For this assignment, there's a few more slides to go through. But basically, I'm not expecting, mass spec always felt the most made up to me. We were taught this before IR and before NMR, and it really just seemed like I was making stuff up.
Okay.
Even more so than IR and NMR. Okay. And when I said to my teacher at the time, like, well, I just make stuff up until it adds up to the right number. He's like, yeah. It's okay that it feels like that because it kind of is that.
Okay.
It's more useful either if you have a database that you're comparing it to, or if you have an idea of what it is, you can use it to support that. It's less helpful in terms of, let's look at this and figure out what it is, unless you happen to get one of these really lucky ones like this. So that's why this is kind of what this assignment is. Or you can count them. So, or I mean, you just look at, okay, there's 60. Yeah, I mean, that's all it really is doing. That it's only in whole numbers. So the spectra that I had to choose from when I wrote this assignment didn't have those peaks labeled for you. When it's blown up a little bit easier, it's a little bit easier to see. So you might open it up on your the file on your iPad or on a computer, so you can zoom in a little bit more and label them yourself. But literally, it's just counting, and they only show up as whole numbers. So
So we can kind of like estimate where it's at and then do some math and figure out what it actually is.
um,
Right?
yeah, right. And by math, I mean counting.
Like the subtraction that we did.
Oh yeah, yeah, exactly. Doing the subtraction is so that you can do things like, okay, 43, you could call that m minus 79
Mhm.
because it's 122 minus 79 gives you 43. So you can label it as that, so that makes it really obvious that you lost a bromine. Or you see a lot of times you'll see m minus 15 because what is 15? A methyl group. M minus 29, you lost an ethyl group. So you can have it labeled like that if it's helpful to you. And that's sort of the things that we're looking for. It's basically, okay, there's a gap here that corresponds to I lost a methyl group, or there's a isotope pattern that makes me really pretty convinced that I've got a bromine. And then you just sort of put those pieces together to see what you get. Mass of 43 is going to, so it did turn out this was 1 bromo propane. 2 bromo propane is going to look really similar, except these heights are going to be a little bit different. What could be I'm going to wait on that question. So here's another example. If you're given the molecule, how can we assign what structures, what fragments are responsible for each of these numbers? What was the mass of 43? Our propyl group, right?
Yeah.
So a propane missing a hydrogen was 43. Where do you suppose you would cut this molecule up to get a propyl carbocation?
Like. Like that after, yeah.
Yeah. Basically, you pick a bond and you cut it into 2 pieces. One's going to be a radical and the other one's going to be a positive charge. And so you should be able to see, okay, I make 1 cut. What can I get? And lone pairs are the most common place to see it cut because lone pairs are bigger, right? And if they're bigger, they're more likely to get hit by those electrons flying through. So the only thing with lone pairs here is a little bit of a cold going around. My house has it too. It's not bad. It's just a runny nose. It's annoying.
Yes.
Yeah. So the most common place for this molecule to get hit is going to be on the oxygen, which means the most common bonds to get chopped are here and here.
So then where did the oxygen show up?
So if we cut here and this turns into a positive charge, that means the oxygen's a radical now.
Right, so it's not going.
It's not going to show up. If it happens to get flipped, then you would get something showing up where that is all the rest of this.
Okay.
So C4H, what is that? 9. So 48, 9 is 57 plus an oxygen is another 16. So something in the 60 range, probably. No, 57 is just this chunk. So, but are you likely to see an oxygen with a positive charge? Because oxygen is more electronegative, right? Oxygen is a radical, still not stable, but it's better than giving it a positive charge and having it missing missing more electrons. So 43 is this chunk. 57 is this chunk. What's 116? Yeah. Whatever the biggest one is almost always going to be the entire molecule where all you do is knock off a single electron, which doesn't even show up as missing anything, right? So 116, what's 101 then? Yeah, got a difference of 15 there, right? So that's a methyl group missing. Which methyl group makes the most sense? Could be one of those. There's two choices there.
But there's the one on the bottom. That one.
Well, those two are identical though, aren't they?
That's true.
So there's two choices that would both give us the same one. It could be this methyl. Do we have a way of differentiating which of those, or they're all gonna be significant contributors, probably, right? So that would be the least likely to do that, because then we get a primary carbocation. We haven't really talked about what it is. Is it still a primary carbocation if it has oxygen attached? We'd want to go look at our stability rules and double check that. Because now we're splitting hairs.
Yeah, so if you're saying it's one of the ones.
It's probably one of these three.
So in this case, things were substituted. Well, like whatever they're attached to being more substituted.
Yes. Is more likely to happen.
What did you say? Like what it's attached to being more substituted, that's the one that's more like. That makes sense.
So this is minus 15. What's 87? That's another 14, right?
Yeah.
So 87 corresponds to losing an entire ethyl group.
Yeah.
So where could we do that?
Yeah, that's one. That's that. Stage 3, stage 2.
Yeah. Because there's nowhere else that you can make a single cut to cut off 29.
It doesn't.
So both, what about this 41 peak? I don't know if you've been paying attention, but 41 is shown up anytime we see 43. 41 shows up also.
Two less.
Two less. I'm going all the way back to the very beginning. 41 keeps showing up as well, right?
Yeah.
But there's not an easy way to just make a single cut to get to 41.
Would it be like?
There you go. Because what if you had 43 positive charge there? What if this went through an elimination reaction? Is that gonna be stable?
I mean, I feel like the top one is,
I guess if I did that, might make more sense.
mm,
What do we have here that we don't have there?
the double bond.
What does a double bond next to a charge do?
Bounces it around.
Bounces it around because of
Electronegativity.
the other one, resonance. This one has resonance stabilization, right? Because there's a resonance structure where the double bond bounces over here, and this is a positive charge,
Yeah.
right? So anytime you wind up with a propyl cation,
Mhm.
if it kicks a couple hydrogens off as H2, you'll also see 41 showing up.
Okay.
We don't really see that with methyls or with ethyls because you need at least 3 carbons to have resonance that way, right? But a lot of these ones that are a little bit larger fragments that are 3 carbons at least, you'll see 57, but then there's also 55.
And so the differences between the hydrogen, that is how the.
Because if you kick off 2 hydrogens, you lose a mass of 2.
Right.
But you gain pi bond that can then rest.
Yeah.
So some of it, like I said, some of it really does feel like just making it up. We got to try and come up with something that could have a mass of 41. And then you just have to be able to justify it. Even if it does, like, I got there because I was just guessing, but now that I've got it up there, oh yeah, it does kind of make sense.
Yeah.
You can come up with your justification sometimes with mass spec after you get the structure. And it's like, okay, well, here is something at least that's 41 that would show up, even though it seems like a stretch. That's a different day. All right. So for this assignment, which you can do anywhere.
Yeah.
It's basically write some definitions, do some vocab. Then answer some questions. 3 is just matching. Here's 4 spectra and 4 molecules. Which molecule goes with which spectra? Several of them have the same mass. If they have a different molecular weight, that's actually a really easy way to differentiate because you can just look at the molecular weight of the highest molecule of the molecular fragment, right? Right. Whatever's furthest to the right. Then there's the isotope peaks, or you can look at the difference between whatever shows up the most.
Here's the EBP ones. Those are on the same.
So there's a lot of somewhat random things that can happen less frequently. We're most interested, there's not really like a set cutoff. This is where we stop labeling stuff.
Last. Even say 5. That's probably the.
That would make sense, wouldn't it?
Because with the other formula.
So you pretty much always want to label the molecular fragment. Because that's going to be your overall molecular weight for the entire molecule.
Right.
So you pretty much always want to label that one. And if your molecular fragment has 2 that are close to the same height.
Wait, there's 15 difference. I would guess like one. There's 15 difference? Think so. If I did my math right. 150 to 175. So then I would guess.
Like 150 and. Between. It's 15 divided by 2.
So
Yeah. So it's in between.
I would guess it's like roughly one,
150.
something like that, 155 to 157.
But you already have a choice. For what these molecules are,
Right.
only one of which has bromine.
Yeah. Like looking at this, you could like we could probably just say, oh, that's the one with different.
Yeah. You don't even necessarily need the peaks labels to answer this question, other than it's going to get tricky to differentiate the middle two from each other because they're going to have the same mass. Or really close to the same mass.
And it's like learning. Is good in progress. What is? And six.
So if OH and NH2 are roughly the same, then fluorine is probably going to be the one at 110. Past 110. Because the other two are pretty similar. Right?
And with the isotopes, there's a 3-to-1 ratio in that parent peak, right? Or sorry, in the molecular fragment.
With yeah.
There's 5, but there's 2 that are most significant, and they're roughly a 3-to-1 pattern.
Yeah. See. Okay.
How do you want us to draw it? Yeah.
And then number 4.
Number 4, here's an IR, here's a mass spec. I'm not going to give you the formula, but you know the molecular weight, and you know how to read an IR. So 2 possible structures. You don't have the NMR, so you're not going to get this is absolutely the structure, but you should be able to narrow it down to a couple good ideas. Yeah. Let's see what I used. I think, if I'm remembering correctly, might have been thymol.
I don't know. I was going crazy because I was like, I would get the 5 signals and then I would recount and I would have like too many hydrogen or something. And I was just going in circles trying to figure out what it was.
Let me.
So then eventually I was like, close enough.
I'm going to stop the Zoom.
Okay.